Alrighty, let's get going. So this is lecture 2.2 on hematopoiesis, kind of a follow-up to last lecture that was on bone marrow. So that was more of a geographical, anatomical lens as into blood cell creation. This is more so deeper into the process of it all. Okay, so now that we have the foundation from last lecture, we can kind of roll into this stuff a little more deep, right? The bone marrow is going to produce, or red bone marrow rather, produces a lot of blood cells for us, but that has an ebb and flow to it, and that's a little less descriptive than I would like. So let's talk about it. The process of making blood, hematopoiesis. So through development, obviously when you are at this stage, you don't have bones. So where do your blood cells come from? Well, as things are developing, we're going to siphon nutrients and support from this egg yolk right here. All right? In the early stages of gestation, we have something called the yolk sac. The yolk sac. So it's very transient, doesn't exist for that long. Its main purpose is just to provide support while placental circulation is established. So we'll have that creating blood cells for us for the first couple weeks, maybe the first month, but it's very piddling. It'll go off, it'll decline very quickly after that. And I'm less concerned about this. I really just wanted you to have this for consistency's sake. This is a more embryological heavy concept, but in the early weeks of gestation, on the developing tubes, so kind of like back here, and then here's another area right here. This is called the AGM region. You don't need to know, but it is the aortal, gonad, mesonephros. So if you really wanted to know that, awesome, but I am in no way going to ask a question on that. I just wanted to include it because I just think it's cool. I just think it's cool. While you're developing, these are all destined to become like tubes of some kind, like the big tube of your heart, the tubes that make up your reproductive tree, and these are the tubes that make up your kidney tree. So all of these are going to become organ tube tissue of some kind. But while you're developing and while circulation isn't established, some of these cells can be like, oh, I'm good. I'm actually going to become a blood cell. A hematopoietic stem cell. This process is something cool called endothelial to hematopoietic transition. So this is something you'll see if you go deeper into embryology. These cells can just kind of code switch whenever they want. Well, I guess not whenever they want, whenever the signals for it is proper. But it's a cool example of something called pluripotency, where these cells can just become, or they have the potential to become very many, many things while we are in this shrimp stage. All right. So not super concerned with that, just a cool idea and to just get you thinking about biology and anatomy in different lights. But this I'm definitely concerned about, okay? So the brunt of fetal hematopoiesis is going to be in the liver, very much so. So as that yolk sac tapers off, the liver is going to really carry the majority of blood cell formation. We will have piddling contributions from the spleen, thymus, and lymph nodes. And at 20 weeks, then we get then we get hematopoiesis as we think about it, which is in the bone marrow. So it'll start in the clavicle. So I have my big muscle man here, the collarbone, the clavicle, and then it'll spread out to the rest of that axial skeleton. So remember, that was the head, neck, and trunk, and pelvis. Okay, so it'll spread to the core, and then as we, after birth and then through puberty on, really, we're going to have a wide distribution of red bone marrow. You're going to find it in all of the long and flat bones. It's very, very common. Okay? So that makes sense, right? The body's developing, the bones are growing, things are constantly in flux. We need as many stem cells and generative properties as possible. Okay? And then the body will start to plateau and reach adulthood. I don't like plateau. Plateau has kind of a negative vibe to it. It reaches its ultimate form. There you go. In adulthood. And then bone marrow is going to kind of shift to axial skeleton only. And I touched on that on the last video. So axial skeleton is these things right here, but here is it picturized. Our head, our vertebral column, our ribs, the sternum, and then the ends of those big long bones, the femur and the humerus, so femur and humerus. Okay? So, in the adult, that's where we're going to find the majority of hematopoietic tissue. But if you're ever confused, boom. Here's the Shangri-La. This chart will have everything that I'm requiring that you know here. All right? So we see in early life, yolk sac starts out real heavy and then drops off rather quick. And during that drop-off, that's when the liver is being generated and formed. And once those liver cells are online, well, then we have the support for some blood cell creation. And the spleen hops in a little bit there, so we see a chunk of it, but the liver's Mac Daddy for blood cell formation in the developing fetus. Then we reach week 20 or so, and the clavicle and then the rest of the axial skeleton kick online, and now my bone marrow is running with the rest of hematopoiesis. All right, so then we split up the bone marrow into the different regions, and we see that the vertebrae and pelvis are going to be kicking well past the age of 70. That is where I'm going to find blood-generating tissue. So the orange right here. Then my sternum, good bit in there, and then the ribs will continue to generate as well. But here's a great example of how that kind of tapers off in the limbs. So my femur, rocking and rolling, right? This is all very high quantity of generation in my 10s and 20s. But by the time I'm 30, likely my femur is not going to be generating that much red bone marrow and thus very little hematopoietic activity. So there's my femur, a big leg bone. Helpful in the beginning, not so much in the later years. And then same with the tibia. But even an even starker drop-off, since it's more distal, it's more down the leg or away from the core. So that's going to have an even quicker drop-off. I didn't label this. I'm very sorry. The white line here, this white line is lymph nodes. They have a piddling contribution as well, but I shouldn't leave it unlabeled. There we go. But I'm more concerned with my bones here. I wanted you guys to see how that isn't always online. It needs to get kicked on as the bones form, and then it's crucial, especially clinically, how you understand where red bone marrow is going to be found. Right? I want you to think about what we talked about last video. Where do we do a bone marrow aspiration or a bone marrow biopsy? So likely it's going to be in one of the very common regions, or the regions that persist within adulthood. It's not the vertebra. We don't want to be stabbing the spine if we don't have to. It's going to be right here, the iliac crest on the ilium of my pelvis. Great place to source bone marrow. A great place. All right, so remember that. Very helpful. All right, now let's go back into the pathways a little more. Nothing too crazy, but I do want you guys to know these because it's also important for understanding different conditions of the blood. All right, so my hematopoietic stem cells, those are the stem cells within my bone marrow that can become any of these blood cells. And they're going to rest in those specialized environments, either in the endosteal niche, it's like the inner surface of bone, or sometimes they'll be in the vascular niche where all the vessels are. All right. When the need arises, signals will tell these progenitors. Progenitors is just a fancy word for the I guess, how do I say this? I guess the top of the tree, the precursors, top ancestor. Okay, they are going to generate these more specialized parts of their tree, but they can become any one of these. So as we go on, as we get these signals, we go down, we pick a path to go down depending on what the stimulus is. The first branch of this pathway is either the myeloid or the lymphoid. We see that over here, myeloid or lymphoid. Lymphoid is more of the adaptive sort of cells, and myeloid is more of my innate immunity, my red blood cells and my platelets. Okay? All right. So on the myeloid pathway, we have my megakaryocyte and erythroid. So that is kind of sectioned off. It's not really sectioned off in this drawing here per se, but if we go down this pathway, it's a bit different from my granulocyte pathway. So we call this the megakaryocyte and erythroid progenitor. All right, so that just means I'm going more so to blood cells and thrombocytes. Okay, so that just means I start down the myeloid path, then I start down the MEP path, and then I can either become a megakaryocyte or an erythrocyte, and that's just dependent on, if you remember from last lecture, if there's EPO telling me, or if there's TPO telling me. Okay, so that's what I mean by those signals. It just depends on what the body needs at that point. If I'm low on red blood cells, my kidneys drop some EPO in the bloodstream, and now I know, well, I need to make some red blood cells. All right, then you have the granulocyte monocyte pathway. So same kind of deal. We go down the myeloid pathway. So now I'm a CMP, a myeloid progenitor. Then I'm a granulomonocyte progenitor. And that can lead to the creation of a neutrophil, a basophil, an eosinophil, or, should have this here as well, or a monocyte. And a monocyte is just the precursor to a macrophage. Okay, so a monocyte is just hanging out in the blood, and then once it goes into the tissue space, then it kind of turns into a macrophage and starts eating stuff up. But we see that those are my granulocytes. They all have all those granules within them. So mostly those innate white blood cells. Excuse me, I'm gonna pardon me. So I don't want you to get too spooked by all of these branches. I think it's easy to get lost in the tree, but it's really not too bad. And I know I've been looking at it forever, so it doesn't mean that much when I say that. But if we just split it, these are more so of just the keeping everything going, like red blood cells, just delivering oxygen, and platelets, making sure I clot well. So that's its own kind of branch. And then all of these are your innate white blood cells. So that's if we need, more fighters present. And then next up is if we need specific fighters present. Okay? So my B lymphocytes, instead of the myeloid pathway, they are going to be selected for and go down the lymphoid pathway. So CLP, common lymphoid progenitor. They then go down this adaptive tree, select for B, and then eventually become antibody factories. We're going to talk about this pathway a lot on Talk 2.4. But we have this development here. Most of it occurs in the bone marrow, and then as they go to their secondary lymphoid organs and learn how to be the best B cell they can possibly be, then they reach full maturity. But all of this occurs in the bone marrow. So very cool. Same deal with the T lymphocytes. We select for that CLP pathway. We become early T cells. But remember, with them, they go to the thymus. So not as much of a bone marrow resident as their B cell brothers are. We are going to talk a bunch about that in Unit 3. The T cell developing pathway is really interesting, and something, if you are med school bound, I literally just took a class where we talked about the different developing pathways and the selection pathways in the thymus. So it's definitely really important to know. So that's a little foreshadowing excitement for you, if you will. And then these weirdos, the NK cells, I told you, right? These are part of the innate system. They are not adaptive, but their lineage, they are from the common lymphoid progenitor, so that makes things a little confusing. So they go down that pathway, but they do not go to the thymus. They do not get educated in the specific way that T cells do. So that lack of education almost produces NK cells. So they're like a very competent high school dropout, right? They don't go to the site of learning all of that specific antigen recognition. They're still competent. They can still operate in the world, but they don't have the honed specific ability that a T cell would have. So they kind of mimic CD8 T cells. And I don't know about you guys. I don't know if I'm losing you or not, but I remember learning these trees and thinking like, well, I don't give a damn. Like, why are we doing all of this? It's kind of boring. But as I got into it a bit more, and I woke up the nerd in me, I have the pathophysiology here is really important. And most of why we want to know this is if we have a failure in one of these progenitors. Remember, that's just meaning a cell that leads to other cells. So if I'm looking in my bone marrow and I'm only seeing CMPs, I'm only seeing these myeloid progenitors, well, then I know I must have a problem with signals that create things down the line. All right? Or maybe I'm only having myeloblasts. These are the precursors to all of my granulocytes here. Well, then I know whatever signal causes these is broken. All right? So this goes back to the bone marrow biopsies and aspirations. If I find a block in any one of these pathways, well, that allows me to diagnose. All right, so that's why this is important. I know it can be a little boring looking at this blood cell tree, but if I know the lineages well enough and I know what triggers the different pathways, then physicians are able to determine what kind of disease or what kind of disease of the blood we are fighting just based off of what blockage that they're seeing in this pathway. So really cool, really cool. We'll talk about leukemia a bunch too. We can have a all myeloid halting or a all lymphoid halting. So that you can imagine is really bad if I'm only stuck up here. Oh my gosh. Then I'm not going to have any functional cells down the river. So that's a really important concept to know. If I'm blocked upstream, these can become anything down here, but they're not differentiated enough to actually perform the physiology that the final product cell is meant to. So that is why these diseases can be so damning, is because you do not have your defenses in play, and when you try to make more, you just make more failed cells. So cool concept to think about. But yeah, so that is hematopoiesis. That's all I want you guys to understand. So just make sure you have a good conceptual understanding of that tree, and then absolutely know that. All right, next is going to be pretty easy. I wanted to just talk about hemostasis, which is the process of blood clotting. So you guys have a full idea of what's in the blood. And then next week is full-on B-cell action. So thank you guys very much for listening. I very much appreciate it.